Hello again, my name is William Pye, and in this video we will be talking about proofs. Previously we covered the rules of inference, which are some common simple arguments. Can we use those small arguments to construct larger chains of reasoning? That is the very heart of building a proof, building that chain of reasoning. Demonstrating the truth validity of an argument can be, and has been done, through truth tables. However, as the number of premises increases, this method becomes increasingly intractable. Basically, it's exponential growth, 2 to 4 to 8 to 16 to 32. It becomes very unwieldy very quickly. In the same way, strings of equivalences can become unwieldy just as much. The algebraic method of rearranging symbols becomes more difficult the more symbols you have. On the other hand, several rules of inference have been established and more facts will be shown to be true in due course. How might these simple results be used to deduce more complex facts? Can I use them like Lego blocks to assemble a larger complex fact out of smaller facts? And this is the central role of proof, using the rules of inference and these other established facts to move from the premises to the conclusion. Before discussing proofs, a key property will be necessary. Previously, it was shown that the conjunction preserves equivalence. That is, if P is equivalent to Q, then this implies that P conjunction with R is equivalent to Q conjunction with R. That is, if P and Q are fundamentally the same, then P conjunction with R is fundamentally the same as Q conjunction with R. This is basically the same as if you say were in algebra and said that x equals y, then this would imply that x plus 3 is equal to y plus 3. It's the same idea. However, the conjunction also preserves implications as well. That is, if P implies Q, then this implies that P conjunction with R implies Q conjunction with R also. So basically, if I swap out the equivalence symbol with the implication symbol, this statement is also going to be a true statement, a tautology. As with the rules of inference, this implication will be established with a string of equivalences. First, I will rewrite the outer implication as negation of hypothesis, disjunction, conclusion in the following way. So, negation of hypothesis, disjunction, conclusion, yielding the following statement. I can then do the same thing with the first implication and the second implication. So I get negation of hypothesis, disjunction, conclusion, and here, same thing, negation of hypothesis, disjunction, conclusion, giving me the following statement. But notice, I have some negations on top of disjunctions and negations on top of conjunctions, so I can apply De Morgan's laws. So applying De Morgan's law here, negation changes disjunction to conjunction, like so. But notice I now have litotes. So by the litotes law, I can rearrange this and make those negations go away, like so. I can do the same thing here. The negation here can distribute over this conjunction, changing it to disjunction. So notice I now have a string of disjunctions here. But notice I still have a conjunction here and a conjunction here with disjunction sitting on top of them. Thus, what I can do is now distribute. This negation P can be distributed over this conjunction here. That is, that the disjunction distributes over conjunction, yielding the following. Negation P, negation P. But notice, P disjunction negation P is the law of excluded middle, which is always true. And true is the identity element for conjunction, so it goes away, leaving me just this statement here. I can do the same thing with the negation R over here. Distribute the negation R over this conjunction, which gives me the following statement here. But notice, negation R, disjunction R is also the law of excluded middle, which yields true, and true is the identity element for conjunction, so it also melts away. But notice, this is all disjunctions, and I have negation Q and Q. Since disjunction is going to be associative and commutative, I can shuffle these to get the backwards Q over here into the front to get me negation Q, disjunction Q, which is also the law of excluded middle, which is always true, but true is the absorbing element for disjunction, so all of the other statements get absorbed into that truth, giving me just truth, establishing the truth of the statement above. With this key property established, what is a proof exactly? This is a question I took a couple months to consider. Several of my mathematics books discuss proofs and even strategies of doing proofs, but never define what a proof is. After reading a few different sources, I found the following definition, which I think is quite functional and concise. So here's what we're going to take a proof to be. A proof is a list of sentences where each sentence comes from one of the following three categories: sentences we assume are true, sentences we already know are true, and sentences we can derive from previous lines. Essentially, a proof is an argument where each sentence can be justified either as a premise or a consequence of previously established facts. for a moment, consider why each of these classes of sentences can be introduced into an argument. Recall that an argument is valid if the conjunction of the premises implies the conclusion. That is, if P, Q, and R are my premises and S is my conclusion, then that means that P conjunction with R conjunction with Q have to imply that S is true. So that's what we're wanting to show. So let's think about sentences we assume are true. Why are these allowed? Well, these are the premises of the argument. So these would be the things that are on the left-hand side. Recall that if a premise is false, then the implication is automatically true. Look at the truth table. If you look at the implication truth table, that anytime the hypothesis, that is the left-hand side, is false, then the implication is automatically true. If one of these premises, say Q here, happens to be false, then conjunction with anything else will yield false, and false implies true or false, and becomes a true statement automatically. Thus, as such, the only interesting case is when all premises are true. Any other case is trivial. Next, let's consider sentences we already know are true. These are the facts that we've already established as being true, like the properties of connectives or the rules of inference. So recall that the truth value T, that is true itself, is the identity element for conjunction. So, that is, if you take a statement P and conjunction with true, then that's equivalent back to P again. Adding in true doesn't affect the statement any. It doesn't add anything new. So, for example, let's consider a statement R. So let's say I know that the statement R is true, that R is equivalent to true. Then let's consider the premises P and Q. What I want to do is I want to add R into my premises list. So why can't I do that? Well, here's why. If I take P conjunction with Q, take my two premises and conjunction them, if I conjunction with true, then that doesn't change the statement. That's the identity property. So P conjunction with Q, conjunction with true, is equivalent to being P conjunction with Q. It doesn't add anything. But wait, I know that R is equivalent to true. So if I take this equivalence and conjunction both sides with P conjunction with Q, remember conjunction preserves equivalence, I get this equivalence as well. That is, R conjunction with P and Q is equivalent to true conjunction with P and Q. Just take this equivalence and conjunction both sides with P conjunction with Q. Thus, I now have that P conjunction with Q conjunction with true is equivalent to P conjunction with Q conjunction with R. But this now gives me a chain of equivalences, and by transitivity, this states that P conjunction with Q conjunction with R is equivalent to P conjunction with Q. That is, R doesn't really add any new information to P conjunction with Q. Thus, I can add or remove R completely freely. So, for sentences we already know are true, I can add them to the premises, and that does not affect at all the truth value of the statement. Lastly, let's consider sentences we can derive from previous lines. This is the case where that key property that we showed at the beginning is now going to be used. So for example, let's say that the premises Q and R imply another sentence U actually occurs. That is, Q conjunction with R implies U is a true statement, that is equivalent to being true. My premises are P, Q, and R. I conjunction them, so P conjunction with Q, conjunction with R. So what I want to do is now conjunction with U. So why can I get away with conjunctioning with U? Well, here's why. As above, I can conjunction with true to give me this statement. Again, true is the identity element, so conjunctioning with it doesn't change its value. Oh wait, the implication is equivalent to true, so as before, I can conjunction both sides of this equivalence with P, Q, and R to give me this equivalence, giving me now that P conjunction with Q, conjunction with R, conjunction with the implication is equivalent to what I started with. And you may see where I'm going now. The reason being is that notice I now have Q conjunction with R, and that's going to be the hypothesis of this implication. By modus ponens, I should now get U here. But there's a problem. What's going to happen is that this statement right here would imply U by itself, and P would come along for the ride by the property that we proved at the beginning. So how do I keep Q and R? I just want to add U into here. I don't want to replace Q and R. So how do I keep Q and R? This is actually where I use one of the properties of the connectives. I use idempotency. Recall that any statement conjunction with itself is equivalent to itself. You can basically duplicate it. Now, usually you use it in a simplification way. That is, P conjunction with P just resolves to being P. You eliminate the duplicates. Here, I want to introduce a duplicate, and here's why. If I introduce a duplicate, Q conjunction with R. Again, that's equivalent to just being Q conjunction with R up here. The two of them merge to become the one. What I'm doing is I'm now splitting it up like this, just duplicating it. So I get this statement now. Well, by modus ponens, Q conjunction with R conjunction with Q conjunction with R implies U by modus ponens would give me just U. But since the conjunction preserves implications, then P conjunction with Q conjunction with R carries down to the next line as well. So I have effectively indeed added U to my hypotheses list. So indeed, P conjunction with Q conjunction with R implies P conjunction with Q conjunction with R conjunction with U. Thus, indeed, any sentence that is logically implied by the previous lines can be freely included. Next, let's consider some examples of proof. This particular exercise comes from the Suppes and Hill textbook. So my premises are P disjunction with Q, negation T, Q implies T, therefore my conclusion will be P. So I could use a truth table, I could use a sequence of equivalences and implications to get this to work, but I'm going to use a formal 3-column proof. If you've taken a course in geometry, this might seem familiar to you. So here's how this works. I take steps. In each step, I make a claim. And in each claim, I must give the reason why I can make that claim. And that reasoning should fall into one of the 3 types of sentences we talked about earlier. So what's my first step? What's my first claim going to be? Well, my first claim will be one of the premises. Specifically, I'm going to take the second premise, negation T. So it's one of the premises. It's one of the sentences we're assuming that is true. So it's fair game. Now, why am I taking the second premise, not the first or the third? Why am I doing them out of order? Well, it's partially because I can. Remember that all these premises will be conjunction together, and conjunction is both commutative and associative. Commutative means I can reorder them however I wish. Associative means I can regroup them however I wish. So I can take them in whatever order I want. Again, some of this is up to personal preference and logical flow. It is up to the author to write something coherent here. So, my first premise here will be negation T. So what's my next statement? Well, my next statement is going to be another premise, specifically the third one. Q implies T. So that's one of the premises. It's one of the things I'm assuming is true, so it's fair game. But now, I have Q implies T and negation T. This is a perfect setup for a modus tollens argument. So using steps 1 and 2 with modus tollens, I get negation Q happens to be true. So this is a statement that is implied by the truth of the previous statements. This is a line that is deduced from the previous lines, and it's fair game too. Okay, so here we go. Here's where we're using the rules of inference. Now, what's my next step? Well, my next step is to introduce the last premise, P disjunction with Q. It's one of the things I'm assuming is true, so it's fair game. So here it is. All right, so now I have P or Q, but not Q. By modus tollendo ponens, that is a disjunctive syllogism using steps 3 and 4, I now have that P must be true, giving my conclusion. Here is a full 3-column proof for this particular argument. Now, for comparison, here's a chain of equivalences and implications that will yield the same result. Again, I take the 3 premises, I conjunction them, and I would show that they imply that P must be true. So what I'm going to do is, as mentioned before, it's commutative and associative conjunction. So I'm going to associate, that is group, the last 2 together. By modus tollens, that would imply that negation Q is true, and by the property that we showed at the beginning, the implication is preserved by conjunction. So I can bring down the P disjunction with Q in the conjunction here. But now, this is going to be modus tollendo ponens, which gives me that P must be true. So here's the conjunction of all my premises. Equivalent, imply, gets me to P. And there is another way of showing it as well. The next example also comes from the Suppes and Hill textbook. My premises here happen to be negation S, disjunction negation R. Negation R implies negation T. Negation S implies P. Negation P. Therefore, my conclusion will be negation T, conjunction negation P. So, what are my steps on this one? Well, I'm actually going to start off with the final premise, negation P, and the penultimate premise, negation S implies P. The reason being is because they both involve P, and it actually sets up a modus tollens argument. Using these two, by modus tollens, I would get negation of the hypothesis, which would give me negation S. Now, it's tempting to use the litotes here, but I actually don't need it. What I'm going to do is now introduce the first premise, which also involves S. So I have negation S or negation R is true, but it's not negation S. So by modus tollendo ponens, that is a disjunctive syllogism using lines 3 and 4, I get negation R must be true. This is where I now introduce the second premise, negation R implies negation T. So this is going to be now a modus ponens argument, giving me negation T using lines 5 and 6. But now I have negation P and negation T, so by adjunction with steps 1 and 7, that now gives me negation T conjunction negation P, giving me the formal proof of this statement. For the last example, let's actually take an English argument, convert it into symbols, and then give a formal proof of it. So my argument here is the following. If I take a train, then I will be late to the conference. If I take a flight or a bus, then I will not be late to the conference. I take a flight, thus I did not take a train. I'm going to represent the sentences in the following way. So P will represent I take a flight, Q will represent I take a bus, R will represent I am late to the conference, S will represent I take a train. So the argument that I give above can be symbolized in the following way. So if I take a train, I will be late to the conference. So if S, then R. So S implies R. My second premise is going to be if I take a flight or a bus, so that is P or Q, then I will not be late to the conference. So P or Q implies not R. So P or Q implies not R. So that's my second premise. My final premise is I will take a flight. So that is P. Thus, my conclusion is I did not take a train. So negation S will be my conclusion. Now that I have this argument symbolized in the following way, what I'm now going to do is give a formal proof of this argument and show that it actually is valid. So my first step is I'm going to actually take the premise P. So I have the premise P. I'm now going to introduce Q with the disjunction using the addition principle from step 1. So now I introduce premise 2, which is going to be this. So P disjunction with Q implies negation R, so that's one of the premises. This sets up a modus ponens from steps 2 and 3 to give me negation R must be true. But now I have negation R, I now take the first premise that S implies R. Well, now this sets up a modus tollens from steps 4 and 5 to give me negation of the hypothesis, negation S, which gives me the conclusion that I'm looking for. Thus, I have a formal proof of this argument. And that's where we'll stop for today. Next time we'll revisit the properties of the connectives and how they might be used in a proof. Below is a list of references for today's video. We have Learning to Reason, an Introduction to Logic, Sets, and Relations by Rogers, and we also have a first course in mathematical logic by Cephas and Hill. If you liked today's video, go ahead and hit the like button below. If you have a comment or question, go ahead and leave that below as well, and we'll respond to you as soon as we can. Thank you for your time, and we'll see you next time. See you then.